Our director says, lights, camera, action.
Yes, right.
Okay, so from here on out, we're going to focus on FDM printing only. If you have questions about other technologies, let's hold them off until after the class, and I'll be happy to spend more time with you. All right, if you look at a 3D printer, an FDM 3D printer, you will see that it really consists of several identifiable components. The number one is the motion platform. It allows us to classify printers into different categories and potentially be able to say something about the printer based on what the 3D motion platform looks like. So probably the most popular machines out there are one of two categories. Either what are called gantry machines, like the two you see in front of you, or our printer. Our printer is also a gantry machine, right? And basically the way it works is that you have a gantry that is either fixed or moving. Like the upper right-hand corner picture has a movable gantry, okay? Or, and potentially have a moving table. The other very, very popular machine are what I call cube machines. They don't actually have to be cubical, they could be rectangular, but it's basically a XYZ cube, okay? MakerBots, Ultimakers, and things of that nature are XYZ cubes. There's a particular flavor of cubicle machine called Core XY. And Core XY machines are different from other cubes in the following way. On a regular cube, there is a single motor that's moving each dimension. There's one motor for X, one motor for Y. Core XY is a very clever arrangement of belts that allows two motors together to control both X and Y. It's tricky. When they spin in one direction, in the same direction together, you're moving in just X. When they spin opposite each other, you're moving in Y. And by having fractionally different relative motion, you can go in X or Y in some very, very precise ways. The upside of that is tremendous. The motors themselves are stationary. They don't move. That's a big plus. That lightens up the machine. The downside is that the belts are long, and therefore the machine is more likely to generate what's called backlash. Backlash in the mechanical system is when a part of the mechanical system is moving in one direction, and you tell it to stop and move in the opposite direction, and it doesn't. It just keeps going a little bit. And then it turns around and catches it. That happens when the system is somewhat flexible. Like a spring, okay? Like a pendulum. It's related. All of that is related. The good thing about it is that it's kind of soft and pliable and it's not going to break easily. The bad thing is that you can't make sharp corners with a 3D printer that has a lot of backlash. You just can't. It won't work. Okay? So there's trade-offs everywhere. Now, there's a number of machines that are sort of less popular but quite interesting nonetheless. There's a bunch of machines called the ARM machines where the table moves in Y, like this. The arm moves in Z, and there's an extruder that runs in X along the arm. The picture you see there, second one from the right in the lower row, is of a machine called the PrinterBot Simple. It's a lovely little machine. It does a perfectly nice job, and for a very long time, it was the least expensive way to get a 3D printer. These days there are less expensive machines, but this is still pretty good. And then there are these wacky things called the Delta machine. They're called Delta because I don't know why. But the way they work is you have 3 vertical tracks, and there are 3 arms. And depending on where the 3 arms are up and down on their tracks, what in the Delta world is called an end effector, which is that extrudery thing down in the middle, moves in the way that you hopefully want. Delta printers are very interesting. They can move very, very fast. So gantry printers typically top out at around 150 millimeters per second of motion. Cubes can typically go to maybe 200 millimeters per second. Deltas have no problem going faster than 300. Okay? So you can print faster with a delta.
And they're also easy to make very tall things.
Yes. The downside of deltas is that they have a very difficult time printing things that are flat, square, rectangular, perpendicular, parallel, engineering kinds of objects. It's possible, but you have to do a lot of work. Whereas gantry and cube and core XY machines are all about making things that are flat, perpendicular, rectangular, parallel, engineering kinds of things. Deltas are really good at making things that are standalone, that don't have to fit with anything else. Cartesian machines are better at making things that have to fit together into a system of components. Why? Because you can make things that are flat, perpendicular, and parallel, and rectangular in a more precise, I shouldn't say precise, in a more predictable way.
Yeah, I thought the precision varies.
It does.
Of course.
It's hard to make an apples to apples comparison, but what you can say is that deltas are less predictable. Okay, other parts of a 3D printer. Well, you have the printing surface, the bed, on which the material is deposited. And then you have the mechanism that does the depositing. Okay? There are two flavors of extruders. There are extruders that are called direct drive, and there are extruders that are called Bowden, or Bowden tube extruders. And the difference is this. All extruders consist of two things. A drive mechanism, which pushes the filament, and a hot end, which actually melts the filament. If the two of them are sitting next to each other on the same subunit, that's called a direct drive. Like there's nothing between the drive and the hot end.
That's these machines.
All of these machines are direct drive.
See the motor right on the printhead?
Yep, that's the drive. Right.
There's a little knurling gear.
So this is your extruder right here. This is the drive portion of it. And down here is the hot end. Okay? Now the hot end itself consists of typically 5 components. And you will learn to know them and love them. Because you will look at them a lot. And when they break, you will replace them. And clean them and curse them. The components are these. There is typically a tube that goes from the drive into the hot end. It is sometimes called a filament barrel, a filament tube. Sometimes it's even called a heat break, and I will explain why in a second. Then there is a squarish block of aluminum called the heating block. Okay? Can you guys find it on your machine over there?
Yeah.
You see where it is? Mm-hmm. Okay. The heating block has 2 things in it plugged into it. One is a heating cartridge, whose function is fairly obvious from the name. And one of them is a temperature measuring device. And there are a couple of different kinds. The one that you will see in your machines today is what's called a thermistor. A thermistor is an electrical component which changes its properties with temperature. It's a thermally sensitive resistor. Okay? So the hotter it gets, the lower the resistance. And then your electronics will understand the temperature of the hot end based on measuring the resistance of the thermistor. Okay. So we have the filament barrel, we have the heating block, we have the heater cartridge, we have a thermistor. And then down on the bottom is the part where the molten plastic actually comes out of, called a nozzle. Nozzles are measured in terms of the final diameter, which is the size of the hole through which the molten plastic comes out of. Right? Common sizes are measured in fractions of a millimeter, like 3.3, 0.4, 0.5, and so forth. Okay? Common sizes are from 0.3 to about 0.5. Larger than that exist, smaller than that exist very seldom. On our printers, for example, we can make extruders with nozzles up to 1.2 millimeters. They're pretty scary because a lot of plastic comes out in a hurry. Okay, I'll give you an example. So this rocket was printed with a 0.5 millimeter nozzle, 0.5 millimeter, okay? And the layer height was about 0.4 millimeter. And this took about 10 to 12 hours. This was made with a different extruder, with a 1 millimeter extruder, with a layer height of about 0.6, 0.7 millimeters. And this took maybe about 3 hours. Now, if you look at it, this is thicker and stronger, but you can really see the layers. You can still see the layers here, but they're much finer. Okay? So, as with everything in engineering, they're straight up. Let's pass that around. Okay. So, we have the 3D motion platform. We have the extruder with all of its components. We have a controller, which is a small computer that runs some software that actually makes the motors move. Okay? And then there's various accessories like mounts and measuring devices and filament feeders and various other things like that. Okay? And that's really the anatomy of your FDM. Any questions? Really?
So finer, so skinnier is finer but slower.
Yes.
Well, finer, but necessarily slower?
Yeah, because you're depositing less volume of material per unit time.
Right, but if you want thinner, then around my head.
And is there any,
When the one was delivered, it comes with the head with about an inch and a quarter piece of,
Filament.
no, it's the Tygon tubing.
No, it's not Tygon, it's Teflon.
Teflon,
Yes.
that's the word I was at. The replacement, and that's just a thermal break between the cold end where the drag gear is and the hot end, just to keep the heat from soaking up through it, right?
So let's talk about this. Okay, let's go back to the picture of the extruder. Okay, and let's talk about the processes that happen there. An FDM extruder is actually a fairly sophisticated bit of engineering.
do a cutaway?
Yeah, we could.
That might help a lot of us.
Okay. That sounds great.
So that we're gonna take the extruder and slice it to see what's going on there.
So here is my filament. Okay. I'm going to go top to bottom. The first thing that happens is a drive. Someplace over here is a gear-looking thing, more round than this. Okay? And typically, although not always, a round bearing that's pressed against it with a spring. Okay? And this gear-looking thing spins in this direction to push the filament down. Make sense? Then comes a transport mechanism, which is a tube. Okay? Then we have the heating block. With a cartridge and a thermistor. Okay? And then we have a nozzle. Here's what happens. This part's hot. Come on. It's hotter than that. This part is hot. And the filaments start melting to the point where this is liquid. And it comes out of the nozzle kind of like that a little bit. All right? And it solidifies. Here's the tricky part. This is running at, let's say, 205C. The last transition where filament becomes soft is 65C. If you allow this part here to be 65C, nothing useful will happen because the filament will just get mushed. Okay? So this part here had better be 25, 35C at the most. So in a span of about 1 inch, you need to drop the temperature 150, 175 degrees. That's hard. So what they do is this. What we do is we play all sorts of tricks to make it work that way. So one of the things that we do, we put in Teflon tubing in here. Which is slippery and stays colder. And then what we do is we blow air on the whole thing with a fan. Okay? To cool it off. On more sophisticated printers like ours, there's actually a water jacket in here that cools it off by having water flow over it. But on the consumer machines, you won't find that. So here's what's going on. That tubing inside is made out of Teflon. For lower temperature printing, that works really, really well. For when you're printing with PLA and ABS up to about 230, 240C, that works. Problem starts happening is if you want to print something more, something a little hotter, like nylon. Nylon, it requires printing temperatures so hot that Teflon inside starts melting. Okay? And so people came up with what are called all metal extruders. All metal extruders don't have a Teflon tube in there, but they blow air much more aggressively. And they try to remove the heat much faster.
The metal tube is going to be conducting heat.
Yep.
Teflon is not a good conductor of heat.
Yep.
Do we have that metal extruder?
So your extruder in these machines are Teflon tube extruders.
Okay. Do you have that one above?
One of the things you will learn is that here are the parts that you will end up replacing on your machine on a regular basis. You will replace thermistors on the average. The first couple of months you won't need to, but after a few months of operation you'll be replacing them at least once a month. And simply because they burn out.
They're running close to their top rated temperature.
That and they are very fragile mechanically.
And is a thermistor, or do you have to buy some specific?
You typically have to buy a specific thermistor. They're called 100 K ohm 2 millimeter NTC thermistors. They cost, I don't know, $1 each on eBay, and they're everywhere, and there's 10,000 different vendors, and you buy the cheapest one and don't worry about it so much. But they're we keep dozens of them around, because they're cheap, and they break down a lot.
How do you know that thermistor's broken down? You don't get any heat.
No, thermistor is a measuring device.
I know.
And the controller is always looking at it. The controller will tell you one of two things. If it tells you that the temperature is 0,
How do you know?
then you know because you're not freezing to death, right? 0 C is water freezing, right? So unless it's water freezing in your house, it's not 0 C. If it's telling you it's 0 C, it's lying through its teeth.
I'm a little chilly.
This is not 0 C. This is about 18. Okay? Number one. Number two, if it tells you it's 500 degrees Celsius in the room, you know that it's also lying through its teeth. Okay? So if it tells you 0 C, it's broken. If it tells you it's 500 C, it's broken. Okay? Some controller systems are smart enough to say min temp, meaning minimal temperature has been reached. That's the same as Z. And sometimes they will also say max temp. Both of those mean that there's something wrong with the thermistor, and we ought to take a look at what's wrong with it. I'll show you how to do it. Okay? So thermistors go, nozzles go. So this is about $1 to $2 part. Nozzles go, and sometimes you want to experiment with different nozzles. There's lots of nozzles you can find out there. They're all very similar.